Welcome to the course on advanced machining processes. We are going to discuss on Mangnetorheological finishing process and Mangnetorheological abrasive flow finishing process. Last class we have discussed on Mangnetorheological finishing process, different component of MRF process, and also we have discussed different component of Mangnetorheological abrasive flow finishing process. Now today we shall discuss about different process parameters, effects of different process parameters on Mangnetorheological abrasive flow finishing process. Okay, so different process parameters already we have discussed. So finishing pressure, extrusion pressure is one of the most important parameter for Mangnetorheological abrasive flow finishing process. Then finishing cycle, then applied magnetic field. Okay, so these three are actually machining parameters you can change from outside. So these three parameters are most important parameters for Mangnetorheological abrasive flow finishing. Other than these parameters are different parameters are concentration of CFP particles and size of carbon in iron particles, and then concentration of abrasive particles and size of abrasive particles or mesh size of abrasive particles, and concentration of base media. So base media in our case we are considering paraffin oil. Okay, so as our experimental setup in MRF process, as our experimental setup, it is made of cast iron. Okay, so there is a corrosion problem. That's why you cannot make water-based media. So that's why we have made oil-based media. Okay, so in that oil-based media, we can use mineral oil. So we have chosen paraffin oil as the base medium, and we have added grease. So grease is added there inside this base media. So 40% is 80% in volume percentage is the paraffin oil, and 20% by volume grease is added. So grease is added actually to increase the viscosity of this media. So it acts as a thickening agent in case of MRF polishing media. So this grease, AP3 grease, it acts as a thickening agent. So whenever this iron particles, its density is higher than this paraffin oil, so that's why it resists the sedimentation problem in case of MRF process. Okay, so with this we are going to start the parametric analysis on in case of MRF process. So these are the different parameters already I have discussed in last class. Okay, so we have considered this kind of workpiece, this length of this or this kind of flat workpiece we are considering. So length of this workpiece is 35 millimeter and width is 5 millimeter and thickness of this workpiece is 2.5 millimeter. So these workpieces are made of stainless steel. So these workpieces are initially pre-grinded. So initial workpiece surface toughness is 0.49 to 0.5 micron. So around 0.5 micron, that initial workpiece surface toughness. So these are pre-grinded workpiece, stainless steel workpiece. Okay, so these workpieces are kept at the internal surface. I have shown earlier. At the internal surface, there are some small slots are there. In that slots, these workpieces are flat workpieces are kept. So it is kept inside a cylindrical workpiece where small slots are there. Okay, so we have considered this is the MR fluid we have considered. So it is given this kind of name MRPF, means Mangnetorheological polishing fluid, with 20% of CS. With 20% of CS, means CS is the carbon iron particles. With different grades are there. So this is one of the grades, CS grade. It has 8 micron average diameter. So we have considered 20% by volume this CS grade carbon iron particles, then 20% by volume silicon carbide abrasive particles with 400 mesh size, and remaining 60% is the base media. So in that base media also 80% by weight is the paraffin oil and 20% by weight is the AP3 grease. So magnetic flux density, so we have a certain limit of magnetic flux density using our electromagnet. So this electromagnet can generate from 0 to 0.574 Tesla magnetic field. So maximum magnetic field available from this electromagnet is 0.574 Tesla. So this magnetic field actually measured at the surface of this core material. Extrusion pressure we have considered from 3 to 4.25 megapascal, or you can say that 30 to 42.5 bar pressure. Okay, so if you consider in bar. Okay, so finishing cycle we have considered 0 to 100 cycles. 0 to 100. So these are the main parameters we are considering with this is the range here. Now response we have to study. So what is the response? So as this is a nano finishing process, we have to consider what is the change in surface roughness. So initial we have measured the initial surface roughness. So after polishing, we have to measure again surface roughness. That is the final surface roughness. This change in the initial minus final surface roughness will give our output. So it is written as del RA. So change in surface roughness is del RA. So that is the response we have studied in our experimental in this experimental study. So first we are going to show what is the effect of magnetic flux density, okay, on change in surface roughness. So you can see here. This is the initial surface roughness. Okay, so 0.49, 0.48, 0.49, and 0.48 again 0.47. Okay, so this is the initial surface roughness of the workpieces, and experiments are conducted at different magnetic fields. So here you can see at 0 magnetic field, then 0.15 Tesla magnetic field, then 0.4 Tesla magnetic field, and then 0.55 Tesla magnetic field, and then 0.57 Tesla magnetic field. So at 5 magnetic field these preliminary experiments are carried out. and at that time other parameters are kept constant. So finishing cycle we have considered at 200 cycles and pressure considered as 37.5 bar pressure. Okay, so for at a different magnetic field, different workpieces are considered. So all the initial surface roughness of the workpieces are considered at the same level. So here almost near to 0.50 micron. Okay, so this red color line, this is the final surface roughness profile. Okay, so now you can see at 0 magnetic field there is no change in surface finish. Okay, so we shall discuss all these things in the next slide. Why we did not get any surface finish at 0 magnetic field. But when we are increasing the magnetic field here, you can see this change in surface roughness here, this blue color line, you can see this change in surface roughness. When we are increasing the magnetic field from 0 to 0.15, then 0.4, then 0.55, then 0.57, with the increasing the magnetic field keeping other parameters constant, you can see this change in surface roughness increases. Okay, so we can see that if we increase the magnetic field, surface roughness improves. So why it improves? Because when we are applying, when we are increasing magnetic field, the CIP particles, they are forming strong chains. Okay, so at 0 magnetic field there is no chains available. So there is no formation of chains. So this is also verified with microscopic image of this polishing media. Okay, so we have seen that without any magnetic field or 0 magnetic field there is no formation of chains. So now when we are increasing the magnetic field, you can see with the increase in the magnetic field, this chain structure actually is stronger, becomes stronger and stronger. So initially these chains are actually columnar structure. Then all these chains will form a bigger columnar structure. Okay, so initially single chains will be formed, and then all these single chains will form a columnar structure, and they will become stronger and stronger. Okay, so this dipole moment also increases with the increase in the magnetic field. So the CIP chains are dipole moment of all individual iron particles also increases. That's why it forms a stronger chain. So when these abrasive particles are held in between this stronger chain, so these abrasive particles, active abrasive particles, will polish with a better efficiency, because they are getting more bonding strength due to the increasing the magnetic field. These abrasive particles will get more bonding strength because these abrasive particles are held in between these chains. They will get more bonding strength. Okay, so that's why with the increase in the magnetic field, this surface finish improves or change in surface roughness increases. So we can say that for the same number of finishing cycles, extrusion pressure and MRP fluid composition, surface roughness reduces with the increasing in the magnetic flux density. Now we are going to discuss what is the explanation. So now you can see here, this is the scanning electron microscope photograph of workpieces at different magnetic field. So you can see here at 0 Tesla magnetic field, initial surface roughness is 0.49 micron. At 0 Tesla magnetic field, this initial surface roughness is 0.49. So you can see here in this figure, so many abrasive marks are there, because all these samples are prepared by grinding operation. So in grinding operation, these abrasive particles make a scratch marks. So these marks are, you can see, lots of peaks and valleys are available in this workpiece. Okay, so these peaks and valleys are available. Now we are increasing to 0.0 Tesla to 0.15 Tesla magnetic field. So when we are increasing to 0.15 Tesla magnetic field, you can see the surface finish improves to 0.44 micron. Okay, so why it happens? You can see here this whatever in initial workpiece surface, whatever these scratch marks, dense scratch marks are there, or in peaks and valleys are there, these valleys are now separated. So in between two scratch marks, two valleys, actually this distance actually increasing here. So now you can see better polishing is obtained in this figure. Now when you are applying higher magnetic field at 0.39 Tesla magnetic field, now these lines, actually valleys, okay, so they are now more separated here. So in between two valleys, whatever these lines are there, in between two valleys, this distance actually increases. Okay, so initially at 0.15 Tesla, these valleys are actually not so much separated, but here we can see here at 0.39 Tesla magnetic field, these valleys are too much separated here. Okay, so now you can see these peaks and valleys are almost removed here. Now you can at 0.5 Tesla magnetic field, you can see these valleys are now too much separated. Now here you can see here exactly at this point, you can see these abrasive marks are there. These abrasive marks are due to the MRFA process. So this MRFA process, in MRFA process, this workpiece lay, this grinding lay, these workpieces are kept in such a way that this grinding lay means along this direction, this grinding wheel is moving. This grinding lay and this MRFA plate, they are perpendicular to each other. In this direction, these lay marks are due to the MRFA process, and in this direction, these lay marks are due to the grinding operation. So these two lay marks are perpendicular to each other. That's why polishing happens so fast. So you can see here these valleys are now too much separated. Okay, so now at 0.57 Tesla, you can see almost it is vanished. These valleys are almost vanished, although little bit of valleys are available here. Okay, so you can see with the increasing the magnetic field how this surface finish actually improves. So all these photographs are taken at the same magnification at scanning electron microscope. All these things are taken at 200x magnification. Now coming to the explanation why it happens with the magnetic field, why this surface finish improves. So you can see here at this first figure, so all these three figures are given at 0 Tesla magnetic field, means you are not applying any magnetic field in this case. Now you know these abrasive particles are surrounded by these CIP chains. Okay, so these CIP chains are forming strong CIP chains are forming, okay, with the application of magnetic field, and when abrasive particles are held in between these CIP chains, they actually give bonding strength to these abrasive particles. So more the stronger the CIP chains, stronger only the bonding strength to the abrasive particles. So now at 0 Tesla magnetic field, there is no chains are available, no bonding strength to the abrasive particles. Here you can see these abrasive particles, it is actually loosely held. So it is not held by these CIP particles, surrounding CIP particles. It is not held by the surrounding CIP particles. Okay. So now this flow in this direction, this fluid is moving in this direction. Okay. So when there is a surface peaks are there, when there is a surface peak is there. Okay. So in that case, when some abrasive particles comes into contact with the surface peaks, because there is no bonding strength to this abrasive particle, so this abrasive particle will try to rotate here. Okay, so as the flow is there, so this abrasive particle will try to rotate here, it is shown in the second picture. Okay, now in third picture you can see this abrasive particle crosses the roughness peaks without cutting the roughness peak, without cutting anything from the roughness peak. So it is just rotate and then it crosses the roughness peak. So like that, because of there is no bonding strength to the abrasive particles by surrounding CIP chains, there is no cutting possible without application of magnetic field. Now the second row, it shows that magnetic field is 0.5 Tesla magnetic field. So here high magnetic field is available here. So now you can see these CIP chains, they are forming chains. So because of this dipole moment, there is strong chains are forming in between the CIP particles. Now when some abrasive particles comes into contact, or it comes in between these CIP chains, they are actually held in between these chains. Okay, so they are held in between these chains. Now there is a flow is there. So you are flowing this media now. So when this abrasive particle comes into contact with the some roughness peaks, okay, so at that time it removes the surface undulations from the it removes the surface undulation from the working surface. Now we can, second picture you can see it removes the small peaks from the roughness, from it removes small chips from the roughness peak here. So here in the third picture you can see it is completely removed. Now effect of extrusion pressure. So this is the initial surface roughness, then this is the final surface roughness plot, and then this is the change in surface roughness plot. From this figure you can see, so from this red figure, the second one you can see here, there is no change in surface roughness, final surface roughness profile, except at 37.5 bar pressure or 3.75 megapascal pressure. Okay, so there is no significant change in surface roughness with the application of pressure in case of MRFF process. But you can see here at 37.5 bar pressure, the surface finish actually improves, and when it goes to at 40 bar pressure, then surface finish again there is an increase in the surface roughness. Okay, so with the increase in the pressure, there is no significant change in surface roughness found from experiments. So all the experiments are carried out at 100 finishing cycles at 0.53 Tesla magnetic field. So optimum pressure, it is means at optimum pressure here it is the change in surface roughness you can see. So maximum change in surface roughness available at 37.5 bar pressure. That's why all the MRFF experiments are carried out at 37.5 bar pressure. So after optimum pressure, you can see again this change in surface roughness decreases. So you can see here, we can give the reason. So you can see from here, this is the wall here, cylindrical wall. You consider cylindrical wall. So we are showing the one half of the cylindrical cross section. So this is the central line. Okay, so this is the wall. Okay, so now MR fluid is flowing through this channel, cylindrical channel. Okay, now first one is the shear velocity distribution. So you can see here velocity, there is a change in velocity profile up to this point, then after that there is no change in velocity profile. So here, from here to here, there is no change in velocity profile. So velocity is constant at this point. So from here velocity is constant. So this constant velocity is called the solid core region or plug flow region, because here because with the application of magnetic field, this MR fluid behaves like a solid kind of thing. So you can see here at this from here to here, there is no change, no shear of the fluid. So MR fluid is flowing like a solid core region. It is flowing like a solid without breaking. Okay. So why it is happening? Because if you plot the shear stress here, shear stress is actually it is maximum at the wall, and it is coming to 0 at the center. Okay. Shear stress is maximum at the wall. It is coming to 0 at the center here. Okay. So shear stress will be high here at the wall. Okay. So this is the plot for the Bingham plastic fluid. So for this Bingham plastic fluid, you can see here, so it is a non-Newtonian fluid. This MR fluid with the application of magnetic field can be considered as a Bingham plastic fluid. Okay, so here there is a shear stress tau 0. This is called yield stress of this fluid. When applied pressure is greater, applied shear stress is greater than this yield stress of this fluid, then only fluid flows, otherwise there is no flow of fluid. So when applied shear stress is greater than yield stress of this fluid, then only fluid flows, otherwise there is no flow of fluid. Okay, so there is a slope of this curve. So this slope of this curve is called eta or plastic viscosity. Okay, so when your applied pressure is greater than your yield stress of this fluid, then only this amount of fluid flows. After flowing, it takes a straight line path. So at that time, the slope of this curve will give the plastic viscosity. Okay, so here coming to this earlier picture, this radius of this solid core region is RP here. Okay, so in this zone, this applied shear stress is greater than yield stress of this fluid. So that's why this fluid is flowing. But in the solid core region, this applied shear stress is less than yield stress of this fluid. So that's why this fluid does not flow in this region. Okay, so there are two methods of machining. One is called, so first one is the condition 1, second one is the condition 2. In first condition, this total solid core actually moving through the cylindrical friction. Okay, total solid core region of this fluid is moving through the cylindrical friction. Now, as the fluid in condition 1, as the fluid is not shear, these abrasive particles will be held with higher bonding force. So as the fluid is not shear, these abrasive particles will be held with higher bonding force. Okay, but in the second case, you can see this fluid is sheared here. So at this zone, this fluid is sheared here. So there is no this bonding between the CIP chains, now it is reduces. Okay, so unless the fluid is not sheared, this fluid will not flow through this cylindrical friction. For this fluid to flow, there it should be sheared. This MR fluid should be sheared. Okay, so here this is the sheared MR fluid here. This is the unsheared MR fluid at the center. So at the center, your shear stress is less, 0, and at the wall shear stress is maximum. That's why fluid actually sheared at the wall only. First, it sheared at the wall. Okay, so here you can see these abrasive particles in the shear zone, it does not have that much bonding force. That's why these abrasive particles can rotate here, it will rotate. Okay, so if it is not able to cut, then it will rotate there in condition 2. Okay, so if we increase the pressure, then what will happen? Your shear zone will be, or yielded zone will be more, and solid core zone or unyielded zone will be less. Okay, so if we don't, if we apply more pressure, then your shear zone will be more, and unsheared or solid core region will be less. Okay, so with the increasing pressure, it happens. So as the shear zone increases, in that zone actually your bonding strength is not strong. Bonding strength to the abrasive particles is not strong. So that's why your surface finish reduces at higher extrusion pressure. So MR fluid can be considered as a laminar flow. So as this fluid is highly viscous fluid, okay, and low shear rate during the experimentation. So it is applied at low shear rate. So that's why MR fluid can be considered as laminar flow. Okay, so another experimental parameter is finishing cycle. So now finishing experiments are carried out at 37.5 bar pressure or 3.75 megapascal pressure, and with a magnetic field of 0.53 Tesla magnetic field. Okay, so these finishing experiments are conducted at 3.75 megapascal pressure and 0.53 Tesla magnetic field. So whatever the final surface roughness obtained from the previous experiment is considered as the initial surface roughness for the next experiment. So like that only in this case, like that only it happens. But in our earlier case, all the experiments are carried out at certain means on a new workpiece, new pre-grinded workpiece. But here, initial experiment means previous experiment, whatever final value we got, so that is considered as the initial for the next experiments. So now again we should tell that one template is actually made to measure the surface roughness at different points on the at different points. Okay, so one template is measured actually to measure the surface roughness at different points on the workpiece, and average value is actually taken for giving the surface roughness, average surface roughness. Okay, so this average surface roughness will give the value of surface roughness from the entire workpiece surface. Okay, so now with the increasing the finishing cycle from 100 to 200 cycle, you can see your final surface roughness reduces. In this case, final surface roughness reduces. But when we are again increasing, means when we are increasing from 200 to 300 finishing cycle, so in that case you can see here again final surface roughness increases. So what is the reason here? Why at the initial few cycles surface roughness improves? Why after that surface roughness deteriorates? Because initially whatever flowed material are there, because these workpieces are actually grinded workpiece. So whatever flowed material or loosely held material, that materials are actually removed by the abrasive particles. So sometimes this loosely held material actually it is deposited on the workpiece surface. So there is a chance that because of these flowed materials are there, it is little bit removed, and it is filled in the oil surface. Whatever valleys are there, it is filled in the valleys. Okay. So that's why initially few cycles you can see your final surface roughness actually improves. But after few finishing cycle, whatever the original valleys are there, peaks or valleys are there, that exposes. Okay. So due to that, with the increasing the finishing cycle, okay, your surface roughness actually again deteriorates, and then slowly it is improving. Okay. So here again this final surface roughness will increase. Okay, because of the leftover materials, because of the cleaning of the leftover materials. Okay, so during that time again with the increase in the finishing cycle, your surface finish improves. Okay, so RA value increases due to the exposure of deep valleys after cleaning of the leftover materials, and initial decrease in the RA value with the number of finishing cycles due to the removal of poured material left after grinding. Now magnetic characteristics of MR fluid. So we shall discuss all these things in our next slides.